Last time, we learned that Newton's laws give us linear, constant coefficient, first-order ODEs for systems with masses. We know that 1, we want to model mechanical systems using masses, springs, and dampers, and 2, real systems, like this slinky, oscillate. However, I told you in lecture 5 that we would use exponential solutions for linear, constant coefficient, first-order ODEs, so that should be true here as well. But how do we get an exponential function like e to the ht to give us cosine and sine terms? The answer is that we use the unfortunately named imaginary numbers. Please don't get derailed by the name. The idea is really simple and magical and very, very cool, and it all hinges on the Taylor series, one of the few things from calculus I said you should remember, and this is the moment you need it. We are going to Taylor expand e to the ht, sine of omega t, and cosine of omega t. So e to the ht is equal to 1 plus ht plus 1 over 2 factorial h squared t squared plus 1 over 3 factorial h cubed t cubed plus 1 over 4 factorial h to the 4th t to the 4th plus more terms. Sine of omega t is equal to, there's no 0th order term, but then we have omega t, and then there's no second order term, but we have a minus 3 factorial omega cubed t cubed, and then there's more terms. Cosine of omega t equals 1, and then minus 1 over 2 factorial omega squared t squared, and then plus 1 over 4 factorial omega to the 4th t to the 4th. You can think of these equations as providing a requirement on h that would imply that h to the 0 should be equal to 1, that h to the 1 should be equal to omega, h squared should be equal to minus omega squared, h cubed should be equal to minus omega cubed, and h to the 4th should be equal to positive omega to the 4th. Moreover, we want to keep even powers separate from odd powers. Now, what function of omega could force these relationships to hold? Amazingly, the choice of h equals j omega, where j is equal to the square root of minus 1, does the job. So if I use this, and I'm going to use a different color so this can be as clear as possible, if I just substitute in j omega for every place that I see h, I'm going to get j omega here, and then j omega squared is equal to minus omega squared. J omega cubed is equal to minus j omega cubed, and j omega to the 4th is equal to omega to the 4th. Now notice that the odd powers have j's and the even powers don't. So we've successfully used j to separate the two groups from each other. If I then write this out, I find out that the exponential is now equal to 1 plus 1 over 2 factorial times minus omega squared t squared plus 1 over 4 factorial omega to the 4th t to the 4th, and then plus j times the other terms. Omega t minus 1 over 3 factorial omega cubed t cubed plus the other terms. This is all equal to cosine of omega t plus j sine of omega t. This formula, e to the j omega t equals cosine of omega t plus j sine of omega t, is called Euler's formula, and you will use it many times while taking this course. Now we get to use Euler's formula anytime that we want to say an ODE has an exponential solution. So I'm going to write down Euler's formula. E to the j omega t is equal to cosine of omega t plus j sine of omega t, so that we have it for reference in the future. So for instance, if I had just our spring mass system, x dot equals minus k over m x, and I assume that I have an exponential solution, x of t equals e to the ht times w, where w is some constant. Then, if I plug that into the differential equation, I find out that h squared e to the ht w is equal to minus k over m e to the ht times w. This implies that h squared is equal to minus k over m, which implies that h is equal to plus or minus the square root of k over m, all times j. This means that x of t is equal to e to the ht w, which is equal to e to the plus or minus square root k over m times j, all times t, times w. Hence, by Euler's formula, we know that this is equal to cosine of plus or minus square root k over m t plus j sine of plus or minus k over m t, and that's equal to cosine of square root k over m t plus or minus j sine square root k over m t. This means we have two possible equations, one with a positive sign and one with a negative sign. Also, this equation still involves j, which we would like to get rid of because x and v are the state variables, and x and v do not involve imaginary numbers. Now remember superposition from lecture 6. If I have two solutions, I can add them together and scale them so that x of t equals cosine of square root of k over m times t plus j sine of square root k over m times t, all times w, is one solution. And x of t equals cosine of square root k over m times t minus j sine of square root k over m times t, all times w, is another solution. If I multiply both by 1/2 and add them, I just get the cosine term. If I multiply both by negative 1/2 j and subtract them, I get just the sine term. So the exponential solution gives me two types of solution, a cosine term and a sine term. So I should expect x of t to involve cosine terms and sine terms, just as we hoped. Moreover, any solution can be written as a constant times the cosine term plus a constant times the sine term. These constants will depend on the initial conditions of the states x and v at time t equals 0. You will learn how to use initial conditions to find these constants in the exercises following this lecture. The main thing to remember from today is that the imaginary number j comes from wanting the exponential function to represent oscillation. With it, we can assume an exponential function is the solution to a linear, constant coefficient ODE and plug into the ODE to obtain a solution.